Hello, welcome to Know About History channel. Hope you like it.
The history of warfare is often written in the blood of soldiers and the strategies of generals, but the success of the greatest amphibious invasion in human history, Operation Overlord, rested as much on the shoulders of civilian engineers and technical innovators as it did on the courage of the infantry. The Mulberry Harbors represent a pinnacle of military engineering, a solution to a problem that many in the German High Command deemed unsolvable: how to sustain a million-man army across a stormy sea without capturing a major deep-water port. After the disastrous Dieppe raid in August 1942, the Allied command realized that the Atlantic Wall was most formidable at the existing ports like Cherbourg and Le Havre. The Germans had spent years fortifying these locations, making a direct frontal assault a suicidal prospect. Yet, the logic of logistics dictated that an invasion force of the scale required to liberate Europe would need thousands of tons of supplies daily: fuel, ammunition, food, and reinforcements that simply could not be landed across open beaches using small craft alone. It was within this strategic vacuum that the concept of the Mulberry Harbor was born, an audacity of engineering that sought to bypass the enemy's strengths by bringing a port with them. The vision began with Winston Churchill's characteristic impatience and foresight. As early as 1917, he had toyed with the idea of artificial islands, but it was in May 1942 that he issued his famous directive to Lord Louis Mountbatten: piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. This was the catalyst for a secret project that would involve over 45,000 workers and dozens of the United Kingdom's leading civil engineering firms. The technical challenges were staggering. The Normandy coast is notorious for its extreme tidal range, reaching up to 7 meters, and its susceptibility to violent North Atlantic gales. Any structure built there had to be strong enough to withstand the pounding of the sea, flexible enough to handle the tide, and yet portable enough to be towed across 70 miles of open water under the constant threat of U-boat attacks and Luftwaffe bombardment. The design that emerged was not a single entity but a modular system of interconnected components, each a feat of specialized engineering. The first layer of defense was the gooseberries, which were essentially breakwaters formed by scuttling old merchant ships and warships, known as corncobs. These provided immediate shelter for small landing craft in the days following June 6. However, the true engineering marvels were the Phoenix caissons. These were massive, hollow concrete blocks, some as large as a 5-story building and weighing over 6,000 tons. They were designed to be towed across the channel and then sunk in a precise line by opening valves to flood their internal compartments. To prevent them from shifting on the sandy seabed, engineers had to conduct extensive surveys of the geological composition of the Normandy shore, a task performed by commandos who swam ashore under the cover of darkness to collect soil samples. The Phoenix units were built in various sizes to match the depths of the water, and their internal structures were reinforced with intricate steel lattices to endure the lateral pressure of the tide. Inside these breakwaters lay the Whale floating roadways. Designed by Brigadier Bruce White and Alan Beckett, these were flexible steel bridge spans mounted on pontoons known as beetles. The beetles were constructed from both steel and concrete, depending on the availability of materials, and had to be designed with a unique torsion capability. Because the sea is never truly flat, a rigid bridge would have snapped under the stress of the waves. The Whale spans were engineered to twist and flex, allowing them to ride the swell while supporting the weight of 40-ton Sherman tanks. The transition from the floating roadway to the solid ground was handled by spud piers, massive platforms with 4 retractable legs that could be jacked down into the seabed, providing a stable, level dock that effectively turned a floating bridge into a permanent pier head. The production of these components was a miracle of industrial mobilization. Because the project was so vast, no single shipyard could handle it. Instead, construction was scattered across the British Isles, from the dry docks of London and Southampton to the shores of the Clyde in Scotland. Thousands of tons of concrete were poured into specialized molds, often in full view of the public, though the purpose of the strange, windowless concrete apartments remained a closely guarded secret. The coordination required to assemble these pieces in the chaotic weeks leading up to D-Day was unprecedented. When the invasion finally began, the towing phase became one of the most precarious naval operations in history. A fleet of over 100 tugboats, many diverted from essential salvage work, struggled against the currents to move the Phoenix caissons at a grueling pace of 4 knots. If a tug was lost or a line snapped, thousands of tons of concrete became a drifting hazard or a sunken loss. Upon arrival at the allocated sectors, Mulberry A at Omaha Beach for the Americans and Mulberry B at Arromanches for the British, the assembly began with surgical precision. The Royal Engineers and Seabees worked under intermittent fire to position the units. By June 18, both harbors were operational, and the flow of supplies began to surge. However, nature would soon provide a test far more severe than German artillery. On June 19, 1944, a great storm of historic proportions struck the channel. For 3 days, the harbors were battered by gale-force winds and massive swells. Mulberry A, located on a more exposed stretch of coast and perhaps less meticulously anchored than its British counterpart, was catastrophically damaged. The Phoenix caissons cracked, and the whale roadways were twisted into scrap metal. The American command decided to abandon the repair of Mulberry A, instead salvaging its remaining parts to reinforce Mulberry B. Mulberry B, often called Port Winston, survived the storm, largely due to the protective features of the Calvados Reef and the superior anchoring of its components. Its survival changed the course of the campaign. While the Germans waited for the Allies to seize a port, Arromanches became one of the busiest ports in the world. At its peak, it was landing 9,000 tons of stores a day. It allowed the Allies to maintain their momentum during the breakout from Normandy, providing the fuel and ammunition necessary for the push toward Paris. The engineers had succeeded in creating an instant harbor that functioned for 10 months, far outliving its intended lifespan of 90 days. The legacy of the Mulberry engineers extends beyond the tactical success of 1944. They pioneered concepts in modular construction and maritime logistics that are still studied by civil engineers today. The use of pre-stressed concrete, the mathematics of wave attenuation, and the development of flexible pier systems all found their roots in the desperate necessity of the English Channel. Beyond the technical, there is the human element, the draftsmen who worked by candlelight, the divers who braved freezing waters to clear obstructions, and the tugboat crews who refused to let go of their burdens. They built a harbor out of nothing, in the teeth of a gale and the shadow of an enemy, proving that the most formidable wall can be bypassed by those who have the imagination to build a bridge over it. Today, when the tide goes out at Arromanches, the rusted remains of the Phoenix caissons still rise from the sand, silent monuments to a time when engineering was the ultimate weapon of liberation. To understand the sheer scale of the engineering effort, one must look at the specific technical requirements of the Phoenix units. Each unit was divided into 6 internal compartments. This was not merely for buoyancy control but was a sophisticated safety feature. If one part of the caisson was damaged by a mine or a collision, the other compartments would keep it stable. The largest Phoenix units, the A1 type, had a displacement of 6,044 tons and stood 60 feet high. The engineers had to calculate the exact amount of water to let in so that the unit would settle firmly on the seabed without tilting or scouring, a phenomenon where the current washes away the sand from under the structure, causing it to collapse. To prevent scouring, they often placed smaller C and D type units in specific patterns to disrupt the flow of the tide. This required a level of hydrodynamic modeling that was entirely manual, using slide rules and hand-drawn charts, yet it proved remarkably accurate. The whale roadways were perhaps the most elegant part of the design. Each span was 80 feet long, and they were joined by sophisticated ball and socket joints that allowed for 3-dimensional movement. This flexibility was essential because the beetle pontoons supporting them would rise and fall with every wave. If the joints had been rigid, the metal fatigue would have caused a catastrophic failure within hours. The engineers also had to account for the weight of the traffic. A convoy of trucks creates a rhythmic vibration that can be just as destructive as the sea itself. By using a combination of steel girders and lateral bracing, they created a dampening effect that absorbed the kinetic energy of the moving vehicles. The spud pier heads, which acted as the terminus for these roads, were essentially the first offshore oil rig designs. Their ability to climb their own legs using massive winches allowed them to be independent of the tide, providing a constant deck height for ships to unload. This innovation alone saved thousands of hours of labor that would otherwise have been lost during high or low tide. The logistics of the corncobs and gooseberries also deserve deeper analysis. The decision to sacrifice older ships was a stroke of pragmatic genius. By scuttling ships like the HMS Centurion or the French battleship Corbett, the engineers created an immediate shelter that allowed the more complex Mulberry components to be installed in relatively calm water. This instant breakwater was crucial during the first 48 hours of the invasion when every second counted. The ships were packed with sand and concrete to ensure they wouldn't shift, and their superstructures were left visible to act as markers and even as anti-aircraft platforms. This layering of technology, from the crude sinking of old hulls to the high-tech flexibility of the whale spans, showed a holistic approach to problem solving. Furthermore, the secrecy surrounding the construction was a masterpiece of counterintelligence. The project was code-named Mulberry, specifically because it was a generic and interesting name. When the Germans saw the massive concrete structures being built along the Thames, they were puzzled. Some German intelligence reports suggested they might be parts of a new type of anti-aircraft tower or even giant storage tanks for a secret weapon to be used against London. The idea that these were mobile pieces of a port was so outside the conventional military doctrine of the time that it was largely discounted. This deception was reinforced by the Allied focus on the Pas de Calais, leading the Germans to believe that any major harbor-related activity would be centered there. By the time the German command realized what the concrete blocks in the channel were, the Mulberry harbors were already being assembled on the horizon of the Normandy coast. The Great Storm of June 19 to 22 remains one of the most studied meteorological events in military history. For the engineers, it was the ultimate stress test. The storm produced winds of force 6 and 7, with waves reaching 15 feet in height. Mulberry's failure at Omaha Beach has been attributed to several factors by modern analysts. The seabed at Omaha was steeper and the sand more fluid than at Arromanches. Additionally, the American engineers had not completed the installation of all the Phoenix units, leaving gaps that allowed the waves to channel and gain speed, creating a Venturi effect that tore the structures apart. In contrast, at Mulberry B, the British had been more methodical in the placement of the bombardon, floating breakwaters, steel crosses that were supposed to break the force of the waves before they hit the main caissons. While the bombardons themselves were eventually destroyed by the storm, they absorbed enough initial energy to save the inner harbor. The lesson learned was that in maritime engineering, the environment is never a static variable. It is a dynamic, often violent participant that requires redundant safety systems. The impact of the Mulberry harbors on the Battle of the Build-Up cannot be overstated. Following the initial landings, the Allied and German forces were in a race to see who could bring reinforcements to the front faster. The Germans had the advantage of an internal rail network, though it was being hammered by Allied air power. The Allies had to rely entirely on the sea. Without Mulberry B, the supply of heavy artillery and tanks would have been slowed to a crawl, potentially allowing the German panzer divisions to contain the beachhead and turn the invasion into a stalemate. The port at Arromanches allowed for the discharge of over 600,000 tons of supplies in its first month alone. It also provided a vital evacuation point for the wounded, allowing hospital ships to dock and take on casualties in a stable environment, which significantly increased the survival rate of Allied soldiers. In the decades following the war, the Mulberry harbors became a case study for total war innovation. They demonstrated that in the modern era, the boundary between civilian infrastructure and military hardware had blurred. The firms that built the Mulberry components, names like Waits, Costain, and Molem, went on to rebuild post-war Britain, using many of the techniques perfected in the secret yards of 1943. The project also highlighted the importance of the Chief of Combined Operations role, which integrated the needs of the Army, Navy, and Air Force into a single engineering goal. It was a triumph of interdisciplinary cooperation. The Royal Navy provided the nautical expertise, the Army provided the labor and the tactical requirements, and the civilian engineers provided the structural ingenuity. As we look back at the engineers who built a harbor out of nothing, we see a narrative of defiance. They refused to accept the geographical limitations of the French coast. They refused to be intimidated by the power of the Atlantic. They took the most basic materials, concrete, steel, and wood, and through the application of physics and organizational genius, they built a gateway to a continent. The Mulberry harbors were not just docks, they were symbols of the Allied commitment to victory at any cost. They represented the belief that no obstacle was too great if it could be measured, calculated, and ultimately, overcome by the human spirit. The rusted caissons at Arromanches, slowly sinking into the sand as the years pass, serve as a reminder that the greatest victories are often won long before the first shot is fired, in the quiet rooms where engineers dare to dream of the impossible. Reflecting on the technical specifics of the Whale bridge spans, it is fascinating to note the role of the Beetle pontoons. These were not uniform. Some were made of steel for durability in deep water, while others were made of concrete to save on precious metal. The concrete beetles were a marvel of thin wall casting, designed to be as light as possible while remaining watertight. The engineers had to ensure that the buoyancy of these pontoons was perfectly matched to the weight of the steel spans they supported. If a pontoon was too buoyant, the bridge would buckle upward. If it was too heavy, it would sit too low in the water, making it vulnerable to being swamped by waves. The balance was so delicate that even the growth of barnacles or the accumulation of salt spray had to be factored into the long-term maintenance of the harbor. This level of detail is what separates a temporary makeshift solution from a masterpiece of civil engineering. The spud piers also featured a revolutionary design. Each pier head was a self-contained unit with its own power plant, winches, and accommodation for the crew. The legs, or spuds, were 90 feet long and could be lowered to the seabed. Once the legs were set, the pier head could be climbed up the legs to the desired height. This allowed the pier to remain level even as the tide rose and fell around it. It was, in effect, a mobile piece of real estate. When the harbor needed to be expanded, additional pier heads could be towed into place and walked into position. This modularity was the key to the harbor's longevity. It allowed for constant repair and reconfiguration without ever shutting down the flow of supplies. The human cost of the Mulberry project is often overlooked in favor of its technical achievements. Hundreds of divers worked in zero visibility conditions to clear the seabed of obstructions and to guide the Phoenix units into place. These men faced the constant danger of the bends, as well as the risk of being crushed by the massive concrete blocks as they were lowered. The tugboat crews, too, worked in a state of exhaustion, navigating through minefields and avoiding German E-boats. Their bravery was essential to the engineering success. Without the delivery system, the most perfectly designed pier was merely a useless block of concrete in a British estuary. The synchronization of these thousands of individuals, most of whom had no idea of the big picture, due to security protocols, is a testament to the organizational brilliance of the Allied planning staff. In the final analysis, the Mulberry harbors were a pivot point in the history of technology. They marked the transition from static engineering, where structures were built to stay in one place, to kinetic engineering, where massive infrastructure could be deployed across the globe. This concept would later inform the development of offshore oil platforms, modular housing, and even the rapid deployment piers used in modern humanitarian disasters. The engineers of 1944 did not just build a harbor, they invented a new way of thinking about the world. They proved that the sea was not a barrier, but a highway, and that with enough concrete, steel, and courage, one could build a path to freedom through the most hostile waters on Earth. The story of Mulberry is the story of how the impossible became operational, and it remains one of the most inspiring chapters in the annals of human ingenuity. The legacy of these engineers is also found in the specific data of the landings. By D+100, 100 days after the invasion, the Mulberry B harbor at Arromanches had handled 25% of all Allied stores, 20% of all personnel, and 15% of all vehicles. These numbers are staggering when one considers that it was a temporary structure intended to last only 3 months. Even after the port of Cherbourg was eventually captured, it was so badly damaged by the retreating Germans that it took months to become fully functional. During that critical gap, Mulberry B was the primary artery of the Allied cause. It provided the heavy equipment that allowed the British Second Army and the 1st Canadian Army to push through the difficult Bocage country and eventually trap the German forces in the Falaise pocket. Strategically, the Mulberry harbors also served as a psychological weapon. When German generals like Rommel and Rundstedt toured the Atlantic Wall, they based their defense on the assumption that the Allies must capture a port. Their entire static defense philosophy was predicated on the belief that without a harbor, an invasion force would wither on the vine. The appearance of a massive, functioning port in a location they had deemed unsuitable for landing was a shock that paralyzed German decision-making in the crucial first week of the invasion. They spent precious time waiting for a second invasion at a port, unable to believe that the Arromanches harbor was anything more than a temporary distraction. By the time they realized the scale of the Mulberry operation, it was too late to dislodge the Allied foothold. The meticulousness of the engineering extended to the very end of the harbor's life. When the war moved deeper into Germany and the ports of Antwerp and Rotterdam were opened, the Mulberry was slowly dismantled. Many of the whale spans were repurposed to replace bombed-out bridges across the rivers of France and Belgium. Some of these spans remained in use for decades after the war, a silent testament to the durability of the temporary design. The Phoenix caissons were left in place, as they were too heavy and too integrated into the seabed to be easily moved. Over the years, they have become an artificial reef, supporting a vast array of marine life, turning a machine of war into a sanctuary for nature. If one examines the technical drawings of the Mulberry project today, the level of complexity is still breathtaking. Each of the hundreds of components had its own identification number and its own specific tow plan. There were instructions for every possible contingency: what to do if a caisson started to list, how to repair a beetle pontoon while it was under a bridge span, and how to use smokescreens to hide the harbor from air observation. The engineers even designed a system of bombardon, floating breakwaters made of steel, which were essentially massive I-beams in a cross shape, designed to float just below the surface and absorb wave energy. Although these were largely destroyed in the Great Storm, the data gathered from their performance helped engineers refine the design of future breakwaters. The Mulberry project was a defiance of the elements. It was a statement that human intellect could overcome the raw power of the ocean. It was a project that required the precision of a watchmaker and the scale of a cathedral builder. The engineers who built it were often anonymous, working in muddy trenches and drafty offices, but their contribution was as vital as any charge up a hill or any dogfight in the clouds. They were the silent architects of the liberation of Europe. Their work at Arromanches stands as a permanent reminder that in the face of tyranny, the most powerful tool is the creative mind. The harbor built out of nothing was, in fact, built out of the collective will of a civilization that refused to be defeated. It was a miracle of concrete and steel, but more importantly, it was a miracle of human cooperation and vision. When we consider the sheer volume of material used, the numbers are nearly incomprehensible for a project built in such a short time frame. Over 600,000 tons of concrete were poured. Over 31 miles of floating roadways were constructed. The Whale Bridge spans alone used enough steel to build a fleet of several battleships. Yet, this massive industrial output was achieved while the UK was under constant threat of V-1 rocket attacks and while its manpower was stretched to the limit by the needs of the armed forces and the coal mines. The Mulberry project was the ultimate expression of the People's War, where every bricklayer and every welder was a frontline combatant in the battle for logistics. The technical brilliance of the project also lay in its adaptability. When the Americans realized that Mulberry A was unsalvageable, the engineers didn't just give up, they pivoted. They shifted their focus to shore-to-shore logistics and used the remaining components to build whale piers at other locations. This flexibility is a hallmark of great engineering. It is the ability to accept failure, analyze its causes, and move forward with a different approach. The survival of Mulberry B and the adaptation of the American logistics plan ensured that the failure of one half of the project did not mean the failure of the whole. This redundancy was built into the very concept of the modular harbor. The story of the Mulberry harbors is also a story of the transition from the British Empire's traditional naval dominance to a new era of technological and industrial might. While the Royal Navy provided the protection and the transport, it was the civil engineers who provided the solution. This shift mirrored the larger changes in the 20th century, where victory in war became increasingly dependent on the laboratory and the factory floor. The engineers of Mulberry were the precursors to the space-age engineers who would later put a man on the moon. They were people who looked at a seemingly insurmountable physical barrier and said, "We can build our way through this." In conclusion, the Mulberry harbors were much more than a collection of concrete blocks and steel bridges. They were the physical manifestation of a strategic breakthrough. They allowed the Allies to treat the coast of France not as a wall, but as a door. By building their own port, they took control of the geography of the war. The engineers who designed, built, and deployed these harbors performed a feat that has never been repeated on such a scale. They transformed the sandy, tide-swept beaches of Normandy into a gateway for an army of liberation. Their work remains a cornerstone of military engineering history, a testament to what can be achieved when science, industry, and military necessity are aligned toward a single, noble purpose. The harbor out of nothing was, in truth, a harbor built out of the very best of human potential, and its legacy continues to inspire those who face impossible challenges today. Expanding further on the technical and analytical side, we must address the specific soil mechanics that the engineers had to master. The Normandy beaches were not uniform. Some areas had quick sand, while others had hard clay or rock. The Phoenix caissons had to be stable on all these surfaces. To solve this, the engineers developed a system of internal ballasting. Once a Phoenix was sunk, they didn't just leave it. They often pumped in additional sand or silt to create a custom foundation inside the concrete hull. This made the unit much heavier and less likely to slide during a storm. This technique is a precursor to modern, gravity-based structures used in the North Sea for oil and gas extraction. The foresight to include these features in a 1943 design is nothing short of extraordinary. The Beetle pontoons also had a specific engineering challenge. They had to be unsinkable in the face of small arms fire. If a German sniper or a stray piece of shrapnel punctured a pontoon, the entire bridge span could fail. To mitigate this, many of the concrete beetles were filled with a specialized lightweight foam or divided into dozens of tiny airtight cells. This meant that even with multiple holes, the pontoon would retain enough buoyancy to keep the roadway above water. This level of over-engineering was what allowed the Mulberry to survive the daily wear and tear of thousands of heavy vehicles. The Spud Piers jacking system was another area of intense mechanical innovation. The jacks had to be able to lift hundreds of tons with absolute synchronization. If one corner of the pier head lifted faster than the others, the entire structure could bind or even tip over. The engineers used a combination of hydraulic and mechanical interlocks to ensure a level lift. These pier heads were so successful that after the war, many were sold to port authorities around the world, and the basic design of the walking, jack-up rig became the standard for the offshore construction industry. The Mulberry Project was, in many ways, the birthplace of modern offshore engineering. Furthermore, the Bombardier floating breakwaters, though often criticized for their failure in the Great Storm, were a fascinating experiment in wave physics. They were designed to float and resonate at a frequency that would cancel out the energy of incoming waves. While they were ultimately overwhelmed by the 40-year storm of 1944, the theory behind them, using tuned mass to disrupt wave energy, is now a standard part of coastal defense engineering. The Mulberry Project was effectively a giant, real-world laboratory where theories of fluid dynamics were tested under the most extreme conditions imaginable. The coordination of the tow was also a masterpiece of maritime management. The engineers had to calculate the drag of each different type of unit and match it to the horsepower of the available tugboats. They had to create tow charts that accounted for the tides in the middle of the channel, which could push a 6,000-ton concrete block miles off course if not corrected. The tugboat captains were given precise lanes to follow, similar to modern air traffic control. This was done in an era before GPS, using only compasses, sextants, and the occasional radio beacon. The fact that hundreds of these clumsy concrete units arrived at exactly the right spot on a 50-mile stretch of beach is a miracle of navigation as much as engineering. Ultimately, the Mulberry harbors represent the triumph of systems engineering before the term was even popularized. It wasn't just about building a pier, it was about the integration of manufacturing, transport, assembly, and maintenance into a single, cohesive system for moving goods. It was the precursor to the containerization revolution that would transform global trade in the 1960s. The engineers of Mulberry realized that the bottleneck was not the sea itself, but the interface between the sea and the land. By building a better interface, they changed the world. Their work at Arromanches was a gift to the future, a demonstration that there is no problem so large that it cannot be solved by breaking it down into its component parts and applying the principles of logic, physics, and perseverance. The harbor out of nothing was the ultimate proof that human beings are not defined by the obstacles they face, but by the ingenuity they used to overcome them. As we dive deeper into the historical analysis of the Mulberry Project, we must also recognize the project management feat. Brigadier Bruce White, who led the technical side, had to manage dozens of competing interests. The Royal Navy was skeptical of anything that didn't have a hull and engines. The Army wanted something that could be built by soldiers, not just specialists. The civilian contractors were worried about their liabilities. White's ability to keep these groups focused on the D-Day deadline was a masterclass in leadership. He famously kept a countdown clock in his office, a rarity at the time, to remind everyone that the tide waits for no man. The secret trial phase at Garliston in Scotland was also a critical part of the story. In the winter of 1943, the engineers built prototypes of the various pier designs and subjected them to the brutal conditions of the Solway Firth. Many of the early designs failed, one bridge span collapsed, and several pontoons were crushed by the tide. But the engineers learned from every failure. They realized they needed more flexibility in the joints and more reinforcement in the pontoons. This fail-fast mentality allowed them to refine the design before the real construction began in earnest. It was this rigorous testing process that gave the Allied command the confidence to bet the invasion on an artificial harbor. The Mulberry harbors also had a profound impact on the post-war landscape. The debris of the project, the sunken ships, the concrete blocks, the twisted steel, had to be managed. But more importantly, the human capital, the thousands of engineers who had learned to solve impossible problems, went on to lead the reconstruction of Europe's infrastructure. They built the bridges, the dams, and the ports that would power the economic miracle of the 1950s. The Mulberry Project was a university of engineering that graduated a generation of builders who knew how to work under pressure and how to integrate diverse technologies into a single goal. In the final reflection, when one stands on the cliffs above Arromanches today and looks out at the circle of phoenix caissons still visible in the blue water, one is struck by the scale of the silence. These massive structures, once the scene of frantic activity and the centerpiece of a global struggle, are now part of the natural landscape. They are a bridge between the past and the present, a reminder of a time when the world was at a precipice and a group of engineers stepped forward to build a way across. They built a harbor out of nothing, and in doing so, they helped build the world we live in today. Their story is a timeless reminder of the power of the human mind to shape the physical world in the service of a greater good. It is a story of concrete, steel, and hope, and it remains one of the most remarkable achievements in the history of human civilization. The detailed design of the kite anchors used for the whale spans also deserves a mention. These anchors were designed by Alan Beckett to dig deeper into the sand the harder they were pulled. Traditional anchors often drag in a gale, but the kite anchor used the force of the storm to secure itself. This was a critical innovation that prevented the bridge spans from being swept away during the Great Storm. Modern versions of these anchors are still used in offshore mooring today. It is another example of how a specific, small-scale engineering solution can have a massive impact on the success of a large-scale project. Every part of the Mulberry, from the 6,000-ton caisson to the 500-pound anchor, was an essential link in the chain of victory. Finally, we should consider the aesthetic of necessity. The Mulberry harbors were not meant to be beautiful. They were gray, brutalist, and functional. Yet, there is a certain majesty in their form. The way the phoenix units echo the shapes of ancient megaliths, and the way the whale spans mimic the skeletal structure of a great sea creature. They are the ultimate example of form following function. They were built for one purpose, to land the goods that would save the world. In achieving that purpose, they attained a kind of rugged, historical beauty that still resonates with anyone who visits the shores of Normandy. The engineers of 1944 did not set out to create art, but in their pursuit of excellence and their commitment to the survival of freedom, they created a masterpiece that will never be forgotten. The sheer volume of the Mulberry operation also involved a massive hydrographic survey effort. Before any caisson could be sunk, the Force Pluto and Mulberry teams had to map the seabed with a level of detail never before attempted. They used early versions of echo sounding and even physical lead line surveys to find every rock and every dip in the sand. This data was then used to create deployment maps for each sector. The precision was so great that when the Phoenix units were finally sunk, they were within inches of their planned coordinates. This level of accuracy was essential to ensure that the whale bridge spans would fit together. If the caissons had been even a few feet out of alignment, the bridges would not have reached their pier heads. This was global positioning, 50 years before the technology existed, achieved through the grit and skill of Royal Navy surveyors. The anti-aircraft capabilities of the Mulberry should also be analyzed. The Phoenix units were not just breakwaters, they were also forts. Each large unit was equipped with Bofors 40mm guns and crews to man them. During the months of operation, the Mulberry harbors were constant targets for the Luftwaffe. The caissons provided a stable platform for anti-aircraft fire, creating a dome of protection over the precious supplies being unloaded. The harbor was its own self-defending entity. This integration of defensive armament into a logistical structure was a foresight that saved countless lives and protected millions of dollars worth of equipment. As a final note on the economic impact, the Mulberry project cost approximately £30 million in 1944, equivalent to over £1.5 billion today. For a project that was only intended to last 90 days, this was a colossal investment. However, when compared to the cost of a failed invasion, both in terms of money and human life, it was the greatest bargain in military history. The engineers proved that logistical insurance is worth every penny. By investing in the Mulberry, the Allies ensured that their greatest military gamble would not be undone by a simple lack of fuel or a summer storm. They bought themselves the certainty of supply, and in war, certainty is the ultimate currency. The engineers who built a harbor out of nothing did more than just move concrete. They moved the very needle of history toward the side of liberation.